Like I said, our plan for today, our agenda for today would be to look at the hard version of the k-means algorithm, how to understand the algorithm and the analysis of the algorithm, then a plain or a vanilla version of that algorithm, okay, aided by a very intuitive formula. It is a fuzzy version of this hard k-means algorithm, and then we will have we will introduce this probabilistic connection and then exploit that connection to enhance the probability model and thereby also design new variants of the k-means algorithm. Okay. So, this is the plan here. So, let us just jump right in and then see what is the hard k-means algorithm, okay, to cluster a set of n objects into k groups. In our case, like I said, we will just have 40 objects into, let us say, k groups using only 2 genes as the data points. The 2 dimension is only as a running example, but it can be any number of dimensions. You can use any number of genes, but we will have 2 genes as our running example. If you ask me, I mean, we are going to look at different aspects of k-means, but if you are in a hurry and you want to know, okay, what is k-means algorithm in one slide, right? This is exactly the hard k-means algorithm, okay? The hard k-means algorithm in one slide or a non-probabilistic version of k-means. It's essentially this. The problem is you want to find k cluster centers. So, this is a centroid based approach. So, you want to find a center for each cluster. So, you want to find capital K number of cluster centers that minimize. So, what is the objective function that it is minimizing? That minimize the sum of squared distance of each data point to the nearest cluster center. Okay, so, this is very intuitive. In clustering, we are always trying to group our objects into different groups, so that within each group the data points are more similar to each other, and then across groups the data points in 2 different clusters are more dissimilar, right, compared to data points within the cluster, right. And so, this is a natural way to formulate this as a formal computational problem. We are finding k cluster centers, but then for each of the centers we want to minimize the distance, in this particular case the sum of the squared distances. So, when I mean distance, these are Euclidean distances. So, you just square your Euclidean distance of each data point to the nearest cluster center, okay. And so, essentially given a set of data points, you need to find these cluster centers, and the algorithm, so this turns out to be for points that are having dimensions greater than 1, and then if your k for general k values, right. So, this turns out to be a computationally hard problem. So, like NP hard problem that we have alluded to before in terms of genome assembly and other things, right. So, this Hamiltonian path problem is NP hard. So, similar to that, this solving this problem exactly is going to be an NP hard problem. So, we resort to a heuristic that's called the Lloyd's heuristic, and this is the hard k-means algorithm. You start with some k centers, we will call it sometimes also referred to as means, that are initialized in some way, okay. They are initialized in some arbitrary way, and then you iterate these 2 steps until convergence, okay. So, you have a set of k centers that you have, they are lying in the same space as the objects you are trying to cluster, okay. So, in this particular case, for instance, one of the center may be here and another center may be here, okay. So, this is center 1 and this is center 2, right. So, you may be starting with some arbitrary data points that is also 2 dimensional, okay. It lying in the same space as all the other objects, and then what you are doing is you assign each data point to the nearest center, right. That is the first step, assignment step, and then once you have assigned this, you need to update your centers. You update your centers to the sample means of the data points they are responsible for, okay. So, in this particular case, again this C1 we will later call it as M1 for mean 1, okay. This we will call it as M2 for mean 2. Then for every data point you can just assign it to the closest center. These data points are closer to this center, first center, than to the other center, and for instance these data points are closer to this center, right. So, this is how you assign all of these data points, and once you have assigned it, then you have to recompute your centers or means, update it to all the points that have been assigned based on whichever is closest to the center, okay. So, those are these 2 steps, very intuitive, very natural, because you have some arbitrary way of initializing your k centers, and then what best way to assign each data point to a center rather than to assign it to the nearest center, right. So, it is very intuitive, a greedy approach in some sense to assign each data point to the nearest center, because that center is going to be responsible for the data point. we are going to use this notion of responsibility like throughout this session. So, this center that is nearest to a data point is going to be responsible for the data point, it's going to be covering that data point, right. And then so every data point is covered by at least, I mean, is covered by one center, right, exactly one center. And then once you have this, then these centers are all now responsible for a set of data points, right. So, then the mean of that would be a better way to cover all of those data points, right, rather than the current value. So, you update your centers to the means of the data points that they are responsible for. Okay. So, those are the two steps. We will look at some examples to see how to understand it even better, and also we will formally also write down the notation so that we are clear about what we mean by nearest, what we mean by closest. We have always seen that we do not want to leave things up to kind of interpretation. We do not want to have any vague explanations. We want to make sure that our algorithms and problem formulations are very concrete. Okay. So, that is a running theme throughout the course. So, let us just stick to that same theme and then say that the input n objects are going to be the set of x1, x2, etc. to x capital N. Okay. The small n is going to be the index for each of these objects, capital N is the total number of objects. Your output is going to be the k centers or means, right, where it is the kth center or kth mean is going to be represented as m with a superscript of k. Okay. So, again you have m1, m2, etc. to m capital K. So, capital K is the total number of centers, small k is going to be the index that runs from 1 through to capital K. Okay. And both of them lie in this space, the same space, right, like I said. In our case, there are two genes, right. So, the I is two dimensional. So, this is just m of k is a vector of two real numbers in our example, x of n also for all n is going to be a set of two real numbers, one for gene A, one for gene B, right. In general, I could be any value 1, 2, 3 or any value that any integer, right. So, you have I is the dimensionality of the data, it is 2 in our example because we just had two genes. Okay. So, what did we mean by the squared distance measure? We said it is the squared Euclidean distance. So, if you look at a data point x and then a mean m, right. So, the squared Euclidean distance is simply go over each of the dimensions little I running from 1 to capital I, right. So, little I goes over every dimension 1 and capital I is the total number of dimensions xi minus mi squared. Okay. So, this is just squared Euclidean distance. So, the square root is removed, but otherwise it is just the Euclidean distance, right. And the problem is find the k means that minimize this sum of squared distances to the nearest center for each data point, right, and that is what is represented as k star of n. Okay. So, d of xn is the nth data point, right, and then you have m of k star of n. So, the k star of n is going to be the k that is the center k that is going to be closest to this data point xn, right. So, and that is what is given here, k star of n is argmin over k d of xn comma m of k. So, you just run over all the values for k running from small k running from 1 to capital K, right, and then you look at whichever is the closest and that k is called k star of n. Okay. So, and then that is what is being minimized here. Okay. So, I hope the problem is now very concretely specified. You have an input, you have the output, you have defined what the squared distance measure is. We will just simply call it as distance d. Going forward, we will drop this squared. The context is clear. Whenever we mean distance, we mean squared Euclidean distance. Okay. So, find k means that minimize this where k star of n equal to this. Okay. So, now having said that, then our algorithm, the problem statement has been formalized, right, using these notations. Then we can also use these same notations to finalize our pseudocode, right. So, to clearly specify our pseudocode. The reason we are being so careful, right, you may be wondering like, okay, it is such an intuitive algorithm, why burden it with all these notations? These notations may appear to be a burden now, but then later on it will be very helpful to see the different variants of the k means. We just have to change one thing here, one thing there, and then slowly we just change one of these equations one at a time, and then you will get more and more generalized versions or better versions of the k means algorithm. Okay. So, it is worth spending some time here with the notations. So, you have the k means clustering, the Lloyd's heuristic is this initialization is you set k means m of k to some arbitrary values. It could be random values or you can do it using some heuristic, right. So, some arbitrary values. So, m of k, k running from 1 to etc. to capital K. Okay. And the assignment step, so you can think about it as the initialization step, and then there is this assignment and update step that has to be repeated until convergence, right. So, these two are repeat until convergence. So, you have the assignment step, which is you are assigning a data point to the nearest center. Okay. So, if m of k is the closest mean to data point x of n, then r k of n, this is called the responsibility, right, of the data point for the data point n, right. So, k is being held responsible for data point n, right, then it is set to 1, but all other centers that are not the closest center or not the closest mean, they do not have responsibility, they do not take responsibility for this data point n, right. So, then that will be 0. Okay. So, this in sense is this this kind of a strict way, right. So, like I only, like every data point is only assigned to one center, that is the closest center, and that is 1, and then everything else it is not assigned. So, there is the other centers do not take responsibility for it. So, then that is 0. Okay. So, this is the assignment. Once you have assigned, then you need to update your centers, like I said, and the updation is just simply the average of all the data points that are assigned to that particular center. Okay. And so, this is written in this way that once you have 1 and 0, right. So, another way to write the same thing will be the following. So, this is the same as sum over all n such that r k of n equal to 1, right, and then you have x of n divided by the size of this, the number of data points that are assigned to this cluster, right. Number of data points for which mean is responsible for. So, this is like the average, right. So, the average or the sample mean. So, this is just all n such that r k of n equal to 1, x of n, and the number of data points for which the particular kth center or kth mean is responsible for is given this notation r of k, where r of k is simply the sum of the responsibilities across all the data points n r little k of n, right. So, this is this r of k is the total responsibility of mean k. In this particular case, it is the total number of data points for which m of k is responsible for, right. The kth center is responsible for the total number of data points assigned to the kth center. Okay. So, I hope that part is clear. So, this is essentially the average of all the data points assigned to this kth center. Okay. Can be written this way, or again for later on we will be using this particular version of the formula, where you just run over all the data points. Some of them r k of n is 0. So, you just exclude those data points, but for others for which it is 1, you just take x of n and then you sum it up and you divide by the total number of data points assigned. So, it is the average of all the points assigned to that particular center. Okay. And then you have to repeat these two steps, because once you update this, then which point is closer to me or farther off from me will change, and then so the assignment will also change. Okay. You keep on doing that until the assignment freezes or the update freezes and no more changes are possible. Okay. So, this should be clearer as we look at some examples, but also I wanted to make sure that the notation is fine. So, if you look at the total responsibility of mean k and then sum it up over all the k centers, right. So, if you look at k equal to 1 to k, 1 to capital K, okay. So, then you will see that it should give you the total number of objects n, okay. Just wanted to make sure that the notations are clear. Okay. This is just to jolt you into understanding what these notations are. Okay. So, if you take the total responsibility, right, so and then sum it up over all of this. So, this r of k sum over k equal to 1 to capital K, right, is going to be sum over k equal to 1 to capital K. R of k is just going over all the data points, right, and then looking at whether this center k is responsible for that data point, right. And then now you can essentially swap these things, these two summations are k of n, right, and this particular value is going to be 1 for each data point, right, because each data point is going to be assigned to the closest mean, and so that is 1 and everything else is 0. So, this will be you will be summing up over a bunch of zeros and then 1 ones here, right. So, then this will be, so this particular one will be 1, okay, this particular box will be 1. So, you will be having sum over n equal to 1 to capital N 1 and that will be n, okay. So, that is what is shown here, okay, sum over k equal to 1 to capital K, R of k is n. It's just a very intuitive thing, but then sometimes these notations can confuse things. So, just wanted to write it out step by step, okay. The total responsibility of mean k is the number of data points assigned to that kth center, and then every data point is assigned to exactly one center. So, if you just sum up all the total responsibilities of all the k centers, you will get the total number of objects capital N, okay. That is it. And now, let us look at these examples. So, you have a set of data points in the 2D again, right. So, we will come back to our exact gene A gene B example, but there are more number of data points here. These green data points which are not assigned initially, and you take two arbitrary values. One of the center is this blue center and another center is the red center, okay. Blue is center 1, let us say, red is center 2. Now, we have the assignment step, right. So, this is the initialization step. So, this is initialization step, this is the assignment step, where you are assigning every data point to the closest center. So, this line tells you that everything on the left of this line is closer to blue and the right of the line is closer to red, right. And so, that is how the data points are closer. So, every data point closest to blue is assigned blue, and then every data point that is closest to the red center is assigned red, okay. Now, like I said, this is going to be covering all of these red points, and it is actually far off from all of these red points. A better way to cover them, a better way to be responsible for all of these data points is to get reassigned to the sample means of these red data points, right. So, then that gets changed here. So, from here it goes into here in the update step, right. So, this is your update step, where the red gets, this is the new red center and this is the new blue center, right. So, that gets updated, and then once you have updated the center, again then the assignments would also have to change, right. So, this is your second assignment step. So, assignment 2 here. In the second assignment step, again, because this blue is here and red is here, you now have a different way, because every data point is now you have to recalculate which is the closest one, and then you recalculate it, and you can see here that now all these blue points are closer to this. So, there are some points that were previously red here, right. So, all this stretch of red, now they are all closer to blue. So, those have been updated, and similarly those that are blue here are now closer to red. So, they have been updated, right. And then again you will have to update your centers. So, the centers are now kind of more in the middle of these data points, right. It's in the centroid of these data points, or the sample means of these data points. So, that is shown here, right, as these big X's. Then again you reassign, there are some things in the border that gets reassigned. So, there were a few blue colors here, right, that has been now assigned red color here. But then pretty much we can see that things are now not changing too much, and in the next setup we are again doing the third update, right. So, this is your update 2, this is your assignment 3, this is your update 3, right. Again you are doing the assignment, so assignment 4, and you can see that things have not changed, right. So, you can see here that in the boundary the coloring remains the same. So, the update 4 also remains the same, and so now you have converged and you stop. Okay. So, this is your grouping of the objects into 2 clusters. So, you have these set of certain number of objects, maybe about 50 objects that are shown here along these 2 dimensions. One is gene A, another is gene B, and then they are grouped into these two clusters with these x's representing the centers of these clusters. Okay, so that is what we seek as output in the k-means algorithm. Let's also look at our very exact example where there are 40 data points and these two genes, gene A and gene B, right? And then look at it slightly in a non-colored version. Okay, so we will kind of use these two versions just to make sure that the point is clearly communicated across. So you have these two centers which are now arbitrarily assigned, and these pluses are the ones which are closer to this center, and the diamonds are the ones which are closer to the second center. Okay. Now you have this assignment step has been done based on which center is closest to each data point. Then you update your centers, right? So this one moves from here to here, and the other center moves from here to here. Then you do another assignment. Now you can see that largely, if you look at the human eye, I can see that there are two clusters largely. So one is this cluster, right? And the other is this cluster. So we are trying to see if the k-means algorithm will converge on what our human brains tell us, what our eyes tell us as clusters, right? So you have this is kind of more or less getting assigned. All these data points are pluses, so they are getting assigned to the first center, and these are all diamonds, and there are some diamonds over here which are closer to this than to this, but that will get fixed in the subsequent update and assignment steps, and after that it stays frozen, right? Nothing else changes. The assignments and updates don't change anything. So you have this set of data points in the first cluster and this set of data points in the second cluster. Okay, so this is another example. Let's look at we are going to understand or analyze the properties of this algorithm. So to do that, I need to show you two more examples. Okay, so please bear with me if you have seen already k-means before. Let's try k equal to 4 clusters, okay, with two different starting points. Okay, this will help us understand the property of the algorithm. I mean, how it works on different data sets, how whether it is sensitive to the initial starting point. Okay, so again we have the same data as before, but instead of 2 clusters, we now have 4 clusters. Okay, and those 4 clusters are k equal to 4, capital K equal to 4. Okay, so these are the 4 starting points. They are somewhat spread apart, right? So 4 of these starting points are spread apart. You run it. You have the assignment and update steps. I am not going to go through each of this, and then you go through these assignments and update steps. I am interested in the final solution. Okay, so if the human eye is asked to, if human brain is asked to kind of group these clusters, if you look at it, then I may say that there is one cluster here, another cluster here, third cluster here, and fourth cluster here, right? And lo and behold, that is what this particular initial set of starting points gives rise to. Okay, so you have this first cluster center and all its nearby points, the second cluster center and all its nearby points, the third cluster center and its nearby points, and the fourth cluster center and its nearby points. Okay, so the diamonds, the pluses, the squares, and the x's are these 4 clusters. Okay, so this seems intuitive enough. Okay, k means with k equal to 4, 4 means algorithm is working fine. But let's look at a different set of starting points. Instead of spreading it out like this, let's say that you are unlucky and then you spread it out so that all the 3 of these initial arbitrary k centers are all in the same space. They are not spread out, but they are all concentrated in one area, and then there is one which is a bit spread out. Okay, so the initial point is the initial points are very different, and then you run this k-means algorithm. You will see that this whole thing is represented as one cluster, right? And then there are these 3 small clusters. So this left hand side has been split into 3 small clusters, and this right hand side has been viewed as one cluster. Okay, and there is no more assignment and update steps you can do here because it freezes, right? So no change in assignment happens, and because of that, no change in the exact locations of these centers also happens. Okay, so this is like the final point, it converges. And that is because you just started out with this non-spread out set of means. Okay, so 3 means are over here, and so they slowly get spread out, but not too much. So those 3 means cover this set of cluster, and the 4th mean just covers this whole set. So it's a little less optimal. I would have liked if it were picking up one cluster here, the second cluster here, and the third here, and the 4th here. Okay, but the initial starting point does change how things are converging. Okay. Okay, so that kind of examples and the descriptions will help us now analyze this algorithm. So is it really solving what k-means problem was set out to solve, right? So the way that we stated the problem, and so what are some of the properties of these algorithms and some of the steps of these algorithms. Okay, properties of this algorithm and some of the steps of this algorithm. Okay, so just to remind you, we want to find k cluster centers that minimize the sum of squared distance of each data point to the nearest cluster center, right? And are the means, right, centroids? So we want to ask these three questions, such as trying to analyze the properties of this algorithm. Are the means or centroids the best and only cluster centers for a given partition? Okay, that is the first question we want to ask. Why do we have the update step updated to the sample mean? Why not take something else like sample median, like taking the median along each dimensions, or some other way of aggregating a set of data points into a single representative point? Okay, why do we want to find the sample mean and take the mean or average of a set of data points assigned to a cluster as the new updated cluster center? Okay, in essence, right, if you want to pose this problem, what I am asking in kind of concrete words is that if you are looking for a data point P, right, in the same space as all the other data points, right. So you may recall that all the data points x of n and the means m of k are all in this real numbers, I vectors of real numbers, right, I dimensional space, right. It's each one is a set of I real numbers, right. Each data point is a set of two real numbers, gene A and gene B. M of k is gene A and gene B also, two real numbers, a vector of two real numbers. In our particular example, in general, it's a vector of I real numbers, right. They are in R to the I. So we wanted to know is m of k equal to argmin of p. So whatever the sample means that we use to update our formula for m of k, right, is it really the point that minimizes the sum of squared distances to all of our x of n's that are assigned to that particular cluster? Okay, so you only go over all the n such that Rk of n equal to 1, meaning that you look at all the data points assigned to cluster k, right, or center k, and then you want to see what is the point that is closest to all those data points, right. So overall, right, so sum of squared distances d of xn comma p, right, and you are looking at the best such point, argmin over p d of x, sum over d of xn comma p, where this n will only run from or run over all the data points that are assigned to this cluster. Okay, and is that really the sample mean that we have computed? Okay, and then the answer will turn out to be yes, and so that is why we do that. And the way to see that is using this objective function, right. So when we look at our objective function, right, it is the sum of squared distances of every data point to the nearest cluster mean, right. And so if you want to write it out this way, you go over all the data points, right, sum over n, right, and then you go over all the cluster centers, and this Rk of n is only going to be 1 for those data points for which the cluster center k is responsible for, right. So you go over all the data points, otherwise it is 0, right. So you only select all the data points for which are assigned to cluster k, right, and then you look at the sum of squared distance between x of n and m of k, right. So this will be your overall objective function that will take the sum of squared distances of every data point to the nearest cluster center. Okay. Now there are many ways to see this. So this objective function, you can verify that it's a convex objective function, and so it will have a unique minimizer, right, and the only minimizer using calculus you can show that it will turn out to be the sample mean or this weighted average, right. So this m of k equal to sum over n Rk of n x of n over R of k. This is the sample mean, or you can also think about it as the centroid, right, or the center of gravity of cluster k. Okay. So you have a particular center p that you want to figure out, and then you have all the data points that are assigned to the same cluster center k, right, and you are now given freedom to change this p wherever you can, so that the sum of squared distances, all of these distances, square of all of these distances is minimized, right. And the best way to put this point p is to put it in the center of gravity of this set of points. Okay, and you can think about it physically or intuitively as each of these data points is connected through some elastic spring, right, to this particular point P, and then you just let it settle in minimum energy configuration, and it will go to the center of gravity of this particular P, okay, and that center of gravity is given by this sample mean formula. This is essentially sample mean of all the points assigned to cluster K, okay, and that follows from standard arguments that this is a convex function, and B you use calculus, right, to take the first derivative of this function, set it to 0, and then see what the values of m that will minimize this objective function to be, okay. We are just fixing our Rk of n, and then we are asking what is the m of k that will minimize this objective function, okay. It will turn out to be this exact formula shown in the update, okay. Okay. So, the means or the centroids are always the best and the only cluster centers for a given partition, okay. So, that is being addressed here. So, we are not getting into the exactly like finding the first order derivative, partial derivative of this objective function with respect to each of the I dimensions of m of k, and then showing this, but we are just pointing it out because you may have seen this k means also earlier in your program. So, we are just reminding you that there is only one minimizer for this. If Rk of n is all fixed, then m of k, this is the best way to update it so that the objective function is minimized, okay. Now, the second question is, does the algorithm always converge for any data set, or can it go in cycles, right? So, because I mean any proper algorithm, any computational algorithm should halt, right? It cannot just keep on going and then not give us any answer at all. So, does this algorithm always converge for any data set? And the answer is again yes. And to show that, we need to we can show it using three things, okay. One is at every step of the algorithm, you are going to say that the objective function that we have just defined in the previous slide, right, the sum of squared distances of every data point to the closest center, right, this objective function. So, at every step, this objective function will decrease, okay. So, for instance, when you go from one step to the other step, the assignment step to the update step, right. So, in the assignment step, in the update step, we are just getting these centers closer to the data points that they are responsible for, right. And so that will definitely because currently it is far off from the set of blue points, and so once you bring it here, it gets closer to all of these blue points. So, the sum of squared distances of the blue points to this blue center will reduce, right. Similarly, the x also here is brought closer to the center of gravity of these red points. So, again this is far off from all the red points. So, the distances, the sum of squared distances are all larger, and then in this new updated x, the sum of squared distances will become smaller, okay. And in the next step also, this is the update step. So, in the update step, the objective function decreases, okay. In the assignment step also, it decreases, right. So, if you find that there are these set of red points which are actually closer to the blue points compared to the red points, then you are just reassigning it to the blue center, right. Similarly, these blue points that were previously wrongly assigned to this red center, I mean to this blue, right, they are now closer wrongly in the sense that according to the previous version it was okay, but with this updated center it is wrong. So, then this blue points will be updated to be closer to the red center, right. So, then they will also be updated, and that also means that the objective function decreases, right. So, every step of assignment and update, the objective function decreases, and when at the point that they do not decrease, right, that is when then you stop the algorithm, because then the convergence has happened, right. If the convergence is not happening, the objective function is always decreasing, okay. And there is two other things that you will have to say. So, the objective function is starting at some value over here, right. So, some value, some initial value. So, objective function is some initial value, right. Let us say, just for arbitrary sake, let us say 100 units, right. So, some 100 units, and then at every step it is becoming smaller and smaller, okay. Maybe it becomes 90 units, maybe it becomes 70 units, and so on, right. Keeps on going, and then we know that it is a sum of square distances. So, it has to be lower bounded by 0. It cannot go below 0, right. and we know that every step decreases it, right. And so you may think that, okay, so number one is that objective function decreases at every step, every assignment or update step, every step of the algorithm. And then B is that the objective function is lower bounded by 0. So you may think that this means that there is a finite number of steps that the algorithm takes, and so it should halt, right, it should converge, there is no other way to go, right. But there is one corner case we have to really understand, which is, let's say that it reaches 50, and then instead of reducing in these bigger amounts, maybe it will just reduce by 50.000001 and then 50.0000 sorry, this is, let's say, 51, okay. So then this may be 50.00001 and then it may be 50.00000 and then it may reduce by this 1 2 3 4 5, right. So 10 to the power minus 5 here, right, and then it may reduce by another 10 to the power minus 5 here, right, and then maybe it reduces by 10 to the minus 6 next, 10 to the minus 7 next, and so you can have like kind of infinitesimal improvements in your objective function. It can still keep on going, right. So then it's not clear that there won't be like infinite number of or a kind of endless number of very small changes, infinitesimal changes that makes the algorithm not converge, right. But we can in fact show that that doesn't happen, because the number of partitions of n objects into k groups is finite, right, finite, and in fact is at most, if you want to have a very rough crude upper bound, right, is going to be at most each object can take one of the k groups as assignment, right. So it's going to be k raised to the power n, right. It's a very huge number, it's an exponential number, but it won't go endless, right. So if you think about these kinds of improvements or decrease in the objective function as very small, like 10 to the minus 5, 10 to the minus 6, 10 to the minus 7, and then it keeps on going infinitesimally small, then you may end up in a scenario where you endlessly keep on running and the algorithm never converges. But then what you can show, what you can see here is that the number of partitions of n objects into k groups is only k to the n, and each one of them have a distinct objective function, right. So the number of steps that you can take, right, will have to be bounded by k to the n, it's finite, right. And so combining all three of these together, A, B and C, you can show that you can see that there is this doesn't go on endlessly, okay, the algorithm has to converge, okay. I hope that part is clear, and so that answers then this question, that does the algorithm converge for any data set? Yes, using those 3 points A, B and C, okay. And this we have already argued, this also yes, using the fact that you have this convex function and then basic calculus, finding the first order derivatives of the objective function and then partial derivatives with respect to the k center, and then using that to figure out what is the best p, okay, you will get exactly the centroid. Finally, does the algorithm actually globally minimize the sum of squared distances? This is an easier argument to make. We just gave you this example that depending on this run 1 where the centers are spread out versus run 2 where the centers are grouped together, you get different answers, right. So what the algorithm is achieving is some form of local minima, right, and it's not finding the global minima. It all depends on the initial starting point, okay. So it doesn't do the global minimization, it only does only local minima, okay. Local minima near your starting point, okay, your initialization point, okay. So that is the analysis of these algorithms, and that is what is summarized here also, and we have already seen this, so I am going to skip this and just make one more comment that, okay, Let me make one more comment that the global minima is not possible to find efficiently. So, it is NP hard or computationally hard problem to find the global minima in a k-means setting, and that is why we have this heuristic that finds the local minima of a particular starting point. Okay. So, you have this whole set of partitions that are possible. Partitions are essentially each data point is assigned to one of the k centers, right, and then the k centers are the centroids of those centroids of the points that are assigned to it, right. So, there are different this is the space of all possible partitions. Okay. This is the space of all possible partitions, and we have said that this is at most k raised to the power n, right. And then you start with one partition, that is your initial partition after the first assignment and update step. Then you just jump into another partition that is better in terms of the objective function drops. Okay, so the objective function decreases in each of these assignment and update steps. I'll just call it a plus u, and then you have another one, you may get something better, and then you get another thing better, right. And you can never come back to the same point again. There won't be any cycles here, because your objective function keeps on decreasing. So, if you go back, then your objective function has to increase again, right. So, this cycles won't happen. So, you will keep on doing it until you hit some local minima, and this is the partition of the data points, n data points into k groups that you are going to output. Okay. If you start somewhere else over this part of the space, so this is some other initial partition, right, initial set of centers that defines an initial partition. You may again have some kind of steps that you take where the objective function keeps on decreasing until you hit a convergence, right, until you hit a point where the assignment and update step does not do anything. Okay. And so, then this will be the local minima if you start from this particular initialization point. Okay. So, depending on where you start, you will hit different local minima. Finding out the global minima among all of these local minimas is an NP-hard problem. Okay. I will stop there, and that would be our presentation of the hard k-means algorithm, or the non-probabilistic version of the k-means algorithm.